Yeah, thank you very much to the organizers for inviting me to this meeting. It's been great to catch up on developments in the field. Also, thank you very much for allowing me to tell people about periods. They're quite my favorite at the moment. So, given the title of the meeting is Motivic homotopy, this may require some explanation. Actually, it is Motivic homotopy in an interaction, and this is very much about interaction. So this is what the interactions are. Here's the stable homotopy category, and to be honest, it doesn't come into what I'm doing, but triangulated motives do. So there's you can go from homotopy category to triangulated motives, but then you can also go to the derived category of Nori motives, and from that you can go to a realization. We'll see that in a few minutes, and then you go to periods. So on the very far end, that's where the periods are. So there is a path from Motivic homotopy to periods. And my talk will start on the right. I'll first start explaining periods. So these are complex numbers. I'm going to tell you what they are and hopefully convince you that they're interesting. And then, you'll learn about this category and how things interact with motives. Tell you about the period conjecture, and then make my way through the diagram to the left, and then we'll see at 10 o'clock how far I have come in the diagram. So that's the plan for the talk. Let's talk about periods. Well, they're complex numbers. I'm working with the convention throughout. All the categories, all the linear categories have Q coefficients. And all objects, motives, varieties, whatever, are defined over Q bar. You could do a slightly more general thing, but that's the most interesting case, so let's stick to Q bar. So periods are numbers, complex numbers that you get by integrating things over other things. And the point of the definition is that both omega and G should be algebraic or arithmetic. So X is an algebraic variety by my convention. This means it's an algebraic variety over Q bar. So it's doubly algebraic. Omega is a global algebraic differential form. Assume it's closed. And then G, the domain of integration, is a semi-algebraic set. So it sits inside the analytic space. So it sits inside the analytic space defined by the algebraic variety. So that's why I'm fixing an embedding of Q bar into C. So I have this analytic space. And in there, we have a semi-algebraic set. And moreover, this semi-algebraic set should be defined. Semi-algebraic means you're allowed to use bigger or equal signs in addition to equalities and polynomials. Okay, people know. But the polynomials should have Q coefficients. So it's also doubly algebraic. It's semi-algebraic and defined over Q in some sense. Okay, then there's no problem. You just integrate, you get a number. These are the periods. Let's do a few examples, because then you'll realize that you have known this all along. So let's talk about GM, A1 minus a point. That's definitely an algebraic variety over Q bar. Then we need a differential form. Let's take dz over z. It's a very nice, has Q bar coefficients, global differential form. And let's, as a semi-algebraic set, let's take the unit circle. So the analytic space of GM, that's C star. And I'm allowed to take anything semi-algebraic in the plane now, so why not take the circle? Actually, take whatever, you always get more or less the same thing. Then you do the integral, and then you get to pi I. Okay?
Yeah, in what sense is S1 defined? I mean, the C star you have to realize as being inside of R squared.
Right, so I'm identifying C with R squared. When I'm talking about semi-algebraic things, you have to have reals, sets over the reals. So C is R squared. So when I'm saying that this is a semi-algebraic set, what I mean is C star is a subset of R squared, and it's semi-algebraic in there.
So if your variety is defined over some number of fields, you have to like take a restriction of scalars?
No. If you have a variety, okay, what are you worrying about? So the Q coefficients, okay, that's because this is semi-algebraic geometry. Whether you work with Q or with all algebraic numbers in R, this doesn't matter. It's the same. You get the same semi-algebraic sets.
I see. So I could imagine my variety inside of some projective space over a Q bar.
Yeah, and you can embed projective space over the complex numbers into some big R to the n as a semi-algebraic set. Yeah. Okay, so 2 pi I is a period number. Yeah, that's what you learned from this computation. And then you probably know that this number is transcendental. This was proved by Lindemann in 1882 in Freiburg. Yeah, actually, I didn't realize this, but Freiburg is very closely tied to the history of transcendence. Next example, let's talk about elliptic curves. So I want my elliptic curve to be defined over Q bar. So let's take an equation. The particular shape of the equation is not so important. I'm taking an elliptic curve in Legendre form, so y squared is some polynomial. And if you look at the corresponding analytic space, then it's genus 1. So the picture of the complex numbers is that one. Okay, this is E of C. Then I need a differential form. Because this is genus 1, there's really only one global algebraic differential form, the invariant differential form. If you want to write it in coordinates, it's dx over y. If you want to write it in terms of the uniformization, so this En was C modulo a lattice. And if you write it in terms of the coordinate on C, then the differential form is dz. It's a global holomorphic algebraic differential form. Okay, that's my differential form. Now I need the semi-algebraic sets. So let's take two closed loops and choose them as generators of the fundamental group. So you can go around like this. This would be gamma 1. And then you can also go around in the other way, like this. That would be gamma 2. So I have two semi-algebraic subsets of this. And then we compute the period integrals. So omega I is a complex number obtained by integrating my differential form with respect to this loop. I get a complex number. And then this is the theory of elliptic functions of the complex numbers. So holomorphic theory. These two numbers actually generate this period lattice. This uniformization is defined by integrating omega, and so things fit together. And that's also why these things are called periods. They appear as periods of integrals of genus 1. Yeah, you get periodicity, and then that's why they're called periods. And then maybe you also know these numbers are transcendental. This was proved in the 1930s by Siegel. So Siegel proved one of them is transcendental, and then Schneider showed they both are transcendental. So you've seen 3 periods now, all transcendental. Let's see 2 more. It's closely related. I'm the same geometric object, still the same elliptic curve, but instead of the differential form omega, I'm using what's usually called eta, x dx over y. It's what classically people call it's a differential form of the second kind. There's only one global algebraic form on the elliptic curve. That was my omega. So this one can't be a global differential form, and it's not. It has a pole at somewhere. But this was allowed in my definition. Just instead of looking at the whole elliptic curve, look at the complement of that pole. That's an algebraic variety. Now we have a global differential form on that complement. It's a form of the second kind because the residue is 0. Yeah? If you have seen these things, then I'm telling you. Otherwise, it doesn't matter. You can do the same integrals. Yeah? Make sure that the pole is not on the path of integration, but then you get those numbers. And they're traditionally called eta 1 and eta 2. And in classical theory, they are called quasi-periods of the elliptic curve. And they are periods in terms of the definition that I gave you. They are also transcendental. This was proved at about the same time that the omegas were proved to be transcendental. But then there is this relation between them. So omega 1 eta 2 minus omega 2 eta 1 is 2 pi I. I didn't choose orientation, so the sign is not completely clear, and then maybe, yeah. But this is the Legendre relation between these period numbers. So what you can see here is, okay, there are relations between period numbers. Okay, if this is the first time that you see these things, what we have learned is periods are interesting numbers. Yeah, usually people are happy when they see 2 pi I. So these are interesting numbers. They are often transcendental. I didn't write down the examples where you get algebraic numbers, but very often they are transcendental. And there are relations between them. And the whole point of this field here in my talk is that motives explain these relations. So that's what I want to discuss. Questions so far? So let's talk about motives and the period conjecture. When I say motives at this point, I guess in my whole talk, I mean Nori motives. It says definition, but it's not a definition. I'm telling you, there is an abelian category of motives called Nori motives. It's the closest abelian category that you can do to triangulated motives. So it has a universal property, and we really very much believe that this should be the true abelian category of motives in characteristic 0. And I'm restricting to the case of motives over Q bar. You can do that for any field characteristic 0. We are restricting to Q bar. What you need to know is that motives have realizations. So every Nori motive has a singular realization. That's a finite dimensional Q vector space. And it has a de Rham realization. That's a finite dimensional Q bar vector space. So over a more general field, that would be a K vector space. It's Q bar because I'm working over Q bar at this point. And these two realizations are always linked by a period isomorphism. So after extending scalars to the complex numbers, singular cohomology and de Rham cohomology become isomorphic. So that's the three things that you need to know about Nori motives.
Do you have smooth variety cohomology?
No, I don't. No, I don't. You can play around with the definitions. Whether you have singularities or not usually wouldn't matter so much, because when you blow up, you make the variety smooth, and then you get just more periods. And
Yes, do you have smooth variety?
yeah, he asked about smooth varieties. You know, you don't have to have smooth varieties.
So you don't have to have smooth.
No, you can use singular. So in my definition, the variety was not assumed smooth. But it also doesn't matter so much. If you restrict to smooth varieties, if you do things right, you get the same numbers.
Yeah, but smooth varieties are in the picture.
Smooth varieties are in the picture, yeah. So in this setting of Nori motives, it's not important whether the variety is smooth or not. It's more important whether it's affine or not. Yeah. So we can encode this the structure having two realizations and a comparison isomorphism into a single category. So some people call it the Hodge-de Rham realization. So let me use that terminology. So for every Nori motive, we have an object in this category of, well, what I call Q bar Q vector spaces. So what I really mean is we have pairs of vector spaces. V-de Rham is a Q bar vector space, a finite dimensional Q bar vector space. VQ is a finite dimensional Q vector space. And phi is an isomorphism between these two vector spaces, but only after extension of scalars. So extend scalars from V-de Rham over Q bar to C, and from V to extend scalars of Q to, oh, this is a typo, this should be C. So extend scalars to C, and then part of your data is this isomorphism over the complex numbers. So it's very similar to Hodge structures, but there aren't any filtrations. So given this data, you can do the following definition. Now we have this isomorphism over the complex numbers, and it's an isomorphism of vector spaces, so it's described by a matrix with entries in complex numbers. And in order to write a matrix, you need bases, so you better do bases in terms of the natural structures that you have. So do a Q bar basis of V-de Rham and a Q basis of Q, and write a matrix in these terms. And then the period space of this Hodge-de Rham structure is the Q bar subspace of C spanned by the entries of the matrix. So the matrix has entries, take the Q bar vector space spanned by them. It's a subspace of the complex numbers. You can do that for any of these Hodge-de Rham structures. In particular, you can do that whenever you have a motive. You have a motive, it has a Hodge-de Rham structure, and then it has periods. There's an equivalent point of view where you don't talk about the period isomorphism, but rather about the period pairing. And in many respects, that's the more natural thing to do. You have an isomorphism of vector spaces. Equivalently, you can say that you have a pairing between one vector space and the dual of the other. I think usually we do it the other way around. We start with a bilinear map, and then we say, oh, but bilinear map is the same as a map from V to the dual of the other vector space. So secretly, the Rham part is the Rham cohomology, and the singular part is singular cohomology, and then the dual of the singular realization is singular homology. So that's a more natural thing to do. We're talking about a pairing between the Rham cohomology and singular homology. So I was integrating, right? So I was looking at numbers where I was integrating. So the G is really a homology class, and the omega is a de Rham cohomology class.
So if you take the cohomology, you take the dual basis given by homology.
Yeah,
then
you get the same.
Then the matrix, the entries are the same entry.
Yes. Whether you take the image of this bilinear map or the entries of the matrix, it will span the same subvector space. It's really an equivalent point of view. Yeah, right. So instead of looking at the vector space spanned by the entries of the matrix, you can look at the vector space spanned by the image of this bilinear map. Exercise. The image of a bilinear map is not a vector space. Not every tensor is an elementary tensor. That's the statement. But if you take the abelian group spanned by it, then it becomes a vector space. And I want my periods to be vector spaces. So I'm looking at the abelian group. With the pairing, it looks a lot more canonical. I don't have to choose a basis. Let's do examples. Wait. So here, if you take the pairing point of view, it's enough to take the abelian group, and then it's automatically a Q-bar vector space. Whereas here, if we take this a bit more elementary or naive point of view, then you take the Q-bar vector space. Yeah. So the point is that Hodge-de Rham, that's already a Q-bar vector space, so you have homogeneity. If you multiply omega by some algebraic number, you stay in this space, and so you can also multiply every period by algebraic numbers. Let's go back to our example. Let's consider GM. The motive of GM, so the interesting motive of GM is the H1. So H1, the Nori motive H1 of GM, that's Q minus 1. So I think there are people in the audience who are more used to triangulated motives than like traditional motives. This is, whether you call this Q minus 1 or Q plus 1 really depends on all your conventions. So I'm talking about cohomological motives, and then Q minus 1 is the right name for this thing. It's it's the Lefschetz motive or the Tate motive, depending on your taste. But we all agree that the singular realization, or rather the dual of the singularization of this motive, is its singular homology. So it's singular homology of the analytic space of GM, so C star, with coefficients in Q. This is a one-dimensional Q vector space, and it's spanned by S1. It's a closed loop. It gives you a class in first homology. So this is the explanation why S1 is the important thing to look at. And the Rham realization, so it's now the first de Rham cohomology of GM. GM is affine, so all de Rham cohomology classes are simply given by differential forms, and this one is spanned by dz over z. So we know that they're isomorphic. They are both one-dimensional, and I've given you bases, and they are in the right. They have the right field of definition. So I want singular cohomology with Q coefficients. Actually, this lives in integral homology, and I want de Rham cohomology over Q bar, and this is actually also integral. And then you look at the period space. By definition, that's now the vector space, Q-bar vector space, spanned by the entries of the period matrix, or by the image of the period pairing. So the period pairing has the multiples of this period integral, dz over z, and we agreed that this is 2 pi 1. So in this case, the periods of this particular motive, they are the multiples of 2 pi I.
Ask a silly question.
Sure.
You represented Q minus 1 as H1 of GM, but that's not the only possible way to represent it.
Yeah, but
you still get the same.
yeah, you always get the same. If it's the same motive, then you always get the same. Yeah, well, no, it's nearly obvious. It's obvious if you know how to compute with cohomology. So if another obvious, well, maybe the actual definition of Q minus 1 would be H2 of P1. Then you have to worry on how do I describe a second cohomology class of S1. So homology is fine, but the Rham cohomology, you have to take an affine cover, and you.
That's why I mean it's not obvious.
Well, there's a general principle that when you have, we'll come to that, but the general principle is that if you have maps of motives, then you also get maps between the period spaces.
Yeah.
Yep, okay. So you have to establish functoriality for the period isomorphism. Yeah, okay. Let's look at our second example, the case of an elliptic curve. So I have the same elliptic curve as before. I have the same generators of singular homology. I called them generators of the fundamental group before, but that's the basis for singular homology. And then we have these classes omega and eta. So omega was dx over y, was the global differential form, and eta was this differential form of the second kind. So the motive I want to consider here is again H1 of an elliptic curve. Its singular realization has this basis, gamma 1, gamma 2. And okay, this is a proper variety, and then you have to worry about what the de Rham cohomology, how do you compute de Rham cohomology of something projective? So It's not affine. You have to cover it by affines and then work it out. So omega and eta are really a basis for this de Rham cohomology. For algebraic curves, the H1 is always generated by the differential forms of the second kind. So they can have poles but no residues. Then they give you classes in the de Rham cohomology of the full thing. In terms of the Hodge filtration, omega is in the one step of the Hodge filtration, and then the eta is in the other. So these two things are a basis for the de Rham cohomology. So you get the period pairing, you evaluate these 4 possible choices. And the period space for this H1 of the elliptic curve is spanned by these 4 numbers. Omega 1, omega 2, eta 1, eta 2 over Q bar. So this is a subspace of C. Its complex dimension is at most 4. But it's not obvious whether it's 4 or 1, right? Yeah, if you want to show that it has dimension 4, say, if you want to show that it has dimension 4, you have to show that these numbers are linearly independent of a Q. It's a non-trivial question. And it's false if the elliptic curve has complex multiplication. So, okay. Now recall the Legendre relation. Same motive, same period space. Then we understand motives of elliptic curves. We've seen a talk here about motives of group schemes. So this is like the starting point of that whole story. In the category of Chow motives, we understand the motive, the full motive of an elliptic curve. And the H2 is actually the second exterior power of the H1. And on the other hand, H2 of a smooth projective curve is always the Tate motive Q of -1. So we have this identification of motives. And this is the Legendre relation again. So you see the Legendre relation, it looks like a determinant. And looks like a determinant because it is a determinant. You have this vector space, and then we take the determinant. Then, this is what shows up. And on the other hand, the periods of this thing are generated by the periods of the Tate motives. So that's 2 pi I. So there has to be this relation. Just because we have a relation between the periods, because we have this isomorphism of periods, and as Mark pointed out, because you have established before that relations between motives give rise to relations of periods, you get this kind of relation.
Do you strictly get that, or something like there's Q coefficient thing?
So this one is completely.
No, I'm sure.
In general,
it's correct, but out of the
in general, no.
Isomorphism up there, do you actually strictly
No,
get that
no,
solution?
you don't. No, you don't. Because if you, I'm working here with a distinguished basis. So in this particular case of elliptic curves, there are like distinguished Z bases that you can do. So this isomorphism, actually, I'm not sure if this isomorphism is true integrally. Maybe it is. But the theory that I'm doing is Q linear, and there's no way to control rational factors. Yeah. No. Okay. This is what the period conjecture says. Period conjecture says that all Q-bar linear relations between periods come about in this way. I've shown you one example where a non-trivial relation between periods is explained by a non-trivial relation between motives. Well, it was established quite a while ago, so maybe now we say this is standard. But the conjecture says this is the only way. Basically, we can't think of anything else, so there can't be anything else. The conjecture is usually called Grothendieck's period conjecture, so everything was started by Grothendieck. He was thinking of the case of pure motives, and all the examples that I've shown you were pure motives. But then you can also generalize to mixed motives in the same spirit. So Grothendieck was thinking of pure motives, and he didn't really write it. So everything that we know about this, the person who explained to us how the conjecture works and, yeah, and how it's related to other things, that's really Yves André. But then you also find papers by Deligne, and then Kontsevich and Zagier had a go at it without mentioning anybody else. And yeah, so it's not, let's call it Grothendieck's period conjecture. And also let's mention Nori, because also he didn't write, but his understanding of what's going on is really behind a lot of the things that are happening now. This looks like rather qualitative and informal. Yeah, what do I mean by all relations? So let me take the time to make this more mathematical. So let's pick a single Nori motive, and then the category generated by this single Nori motive. So what I mean by this is I'm taking the full subcategory closed under sub-objects, yeah? But generated by a single object. Then for this category, I get formal periods. It's this P tilde. What I do, I take this tensor product, the Nori motive. So every Nori motive in the category has a singular realization and a de Rham realization, and I take this tensor product between the de Rham realization and the dual of the singular realization. So these are the things that would evaluate and give periods, but I'm just taking the tensor product here. And then there's an equivalence relation. So I'm describing a vector space by generators and relations. And the relations, they are induced by morphisms in my small category. So whenever I have a morphism of motives, I get a map on the de Rham realization, and I get a map on the singular realization, and so there is a connection. It takes the shape of like a projection formula. So you have, because I have the dual here, it has functoriality in the other way.
So it's like a co-equalizer between the n and the n prime, mapping in two different ways. Is that what it is?
No?
What's the relation?
The relation, okay. Oh, wait, no, I mean, the relation is, okay, that's what you mean? Okay, this is the kind of relation. And then I would say that the tensor, W tensor F lower star sigma is equivalent to F upper star. And now I'm not sure about upper and lower star because there are too many contra and covariant things in there. But that's the shape of relations that we have. And we get these relations for all morphisms in the category. So these are the relations induced by functoriality of motives. And we put them all into this space of periods here. So whenever we have a formal period, we can evaluate and we get a complex number. And then you think about this for 5 minutes, and then you see that if you start with a formal period of M, then you'll end up with an actual period of N. If you have a submotive, then the periods of N are contained in the periods of M. There's nothing new. So you get just the periods space of M as the, wait. You get the period space of M as the image of the evaluation map. So we have this surjection from formal period to actual period. And then you think for another 5 minutes and you see that the map from here, just the pairing just for M to formal periods of M is also surjective. So you have enough relation that every formal period of a sub-object or of a sub-quotient actually comes from a formal period of M. So we have this little chain. This is a finite dimensional vector space of a Q bar. So it's pretty small, the whole thing. And then the period conjecture in this case says that this map should be an isomorphism. All relations between actual periods are the ones that you already have in formal periods. That's the period conjecture. You can use this as a statement, as a precise formulation of the period conjecture, or if you start with some other formulation, then it would be a proposition that it's equivalent to whatever you know. Asking this map to be bijective or to be injective is the same, because it's obviously surjective. Oh, that's a precise formulation of the period conjecture for M, and then you can ask that for all motives, and then you have the period conjecture for the category of motives. What do we know? We have motives of projective spaces. Motive of projective spaces, this is Tate twist, Qn for n in the integers. And the periods of Qn, that's 2 pi I to the minus n, so you get powers of 2 pi I, or get powers of I. And there aren't any relations between those motives. So the prediction of the period conjecture is that all these numbers are Q-bar linearly independent. That's the same as saying that pi is transcendental. So this is Lindemann's theorem, okay? Motives of projective space are fine because pi is a transcendental number. And you can see how things fit, how the formalism of pure Tate motives fits together to that statement. The only other case, if I understand this correctly, the only other case of where we understand the full motive of an algebraic variety is the case of CM elliptic curves. When I say H star, then I mean H0 plus H1 plus H2.
You don't take the tensor algebra generated by the...
I don't take the tensor, okay.
So you just
So if you take the tensor algebra generated by H1 of an elliptic curve, then you get the abelian category generated by this thing.
Oh, it's the same thing.
It's the same. So the tensor algebra generated by H1, the second tensor power is Q minus 1, and the second exterior power, and yeah. So these two statements are the same. Yeah.
Wait, can you say that again? The tensor algebra generated by H1 of an elliptic curve is the same as the abelian category generated by H star?
Yeah, I think so.
That cannot be true, because in the tensor algebra you're going to have motives of arbitrarily big weight.
Yeah, you have all the Q of minus.
Okay, right. So I also get all the powers of Q of I. Yeah. Okay, it's not the same. It's not the same category, but the period conjecture is the same. That's, the period conjecture is the same. Wait, do I know this? You're not convinced.
We can talk about that.
So I certainly stand by my original statement that the only case where we understand the full motive of an algebraic variety and know what the period conjecture is true is in the case of CM elliptic curves. So note that it's open for arbitrary elliptic curves. Chudnovsky proves an upper bound, and in the CM case we know that the he proves a lower bound, and in the CM case the lower bound and the upper bound agree. In the CM case you have an additional morphism of varieties from the complex multiplication of the elliptic curve. So it creates new relations, makes the period space smaller. So we know this case.
So it's not known for H star e to the n, with e is equal to CM. That would be like asking for the tensor algebra. If you do this for all n.
I have to think about this. So Chudnovsky proves it in terms of the transcendence degree of the field that you get. So I think he does tensor powers of E. Yeah. Oh, sorry. Then I was wrong. I was wrong. There's some intermediate cases that we have, but then basically the only big class of motives that we have is one motives. It's I did this only a few years ago together with Stolz. So the period conjecture holds for one motives in this sense that I told you. I'm not making claims about the transcendence degree. I'm just making claims about the span.
What do you mean one motive?
One motive. It's the H1 of an algebraic variety, or the motive of a curve.
So all kinds of one motives.
All kinds of one motives. Yeah, any one motive. So far, what I was discussing was the period conjecture. So what motives make predictions about periods? And now I want to go the other way around. I want to talk about this. Oh, wait, no, this doesn't work. Okay, up there, it's not a proper. We have this functor from Nori motives to these Hodge-de Rham things. We were using this functor in order to formulate the period conjecture, but now I want to understand this functor better. Okay, here's the statement. If the period conjecture holds, then this functor is fully faithful with image closed under subquotients. The faithfulness is not really a statement. This is basically the definition of Nori motives. Nori motives are defined in a way that they are a subcategory, a non-full subcategory of the category of Q vector spaces, and it factors. So the faithfulness is by definition. So the claim here is that whenever you have a morphism between Hodge-de Rham structures, it actually comes from a morphism of mixed motives. So this has very much the flavor of the Hodge conjecture or the Tate conjecture. And Yves André was the one who really propagated this, yeah? That we should think of the period conjecture also in terms of fullness as we think about all the other fullness conjectures. This statement is not hard to prove. I can give you the idea. So here, this thing on the left is my definition of the formal period space of M. We have this vector space, and then the relations coming from morphisms of motives. And it has a surjective map to the actual period space. And then I can put something in the middle, which looks very much like the formal period algebra, but doesn't use motives, but rather these H-de Rham structures. So instead of working with a full subcategory of M, I'm working with a full subcategory of these Hodge-de Rham structures, but otherwise do the same thing. Yeah, take all sub-objects, all sub-quotients, and then the relations are now induced by morphisms of Hodge-de Rham structures. And that's obviously then surjective too. That's the period conjecture. The period conjecture says that the composition is injective. So if the period conjecture holds, then this map here, the first one, is also injective. So there can't be any new relations. If there was a new relation, a new morphism in Hodge-de Rham realizations, there's no room for that. Okay, that's not a complete proof, but the complete proof is not very much different from what I said. There's simply no room for new relations because new relations are seen by periods. And the period conjecture says the only relations come from motives.
And the N and the HM, those are all subquotients, or there might be more of them?
So they are subquotients of additive powers of M.
No, I mean in the H of M.
On the right, what do you mean? Yeah. Here? Oh, there are more N.
There are more N's than just...
A priori, there would be more N.
Okay,
yeah.
That gives you this extra some N that might be possible. Because the image closed under subquotients would kind of suggest that...
Yeah, right. Yeah. Yeah, that's...
Great. Oh, okay.
You prove it the other way around. You first prove that the image is closed under subquotients, and when you have an exact functor and the image is closed under subquotients, then it's full. That's just general mechanism. So you have to actually prove something about the objects rather than about them. Yeah. Okay, so this is the insight. If the period conjecture holds, then we know this functor to be fully faithful. So an obvious question is, do we have the converse? So if the functor is fully faithful, do we get the period conjecture? And to that, the answer is really a resounding no, it's not. The period conjecture is infinitely more difficult than this fullness. And in this sense, the period conjecture is a lot harder than the Hodge conjecture. So just gives you an idea how bad this is. Let's look at the example. So here, this is a particular Hodge-de Rham structure. It's a two-dimensional thing, so it has a two-dimensional Q-bar vector space, two-dimensional Q vector space, and then an isomorphism between the complex vector spaces. So I'm giving you a matrix. And this matrix looks bad, and that's why it is bad. Okay, then you compute. This is linear algebra. You compute, this object is simple. It doesn't have any substructures. Substructure would have to be one-dimensional. There's no way to put this matrix into triangular shape, at least not with the base changes that you're allowed to do, which have to respect the Q-bar and the Q structure. Okay, so you check that this object is simple because log 2 and pi and 1 are linearly independent over Q-bar. So use transcendence theory to understand that this is true. And you also compute the endomorphisms of this simple object. And the only ones that you get are the diagonal matrices. It's Q. So there aren't any relations in the category generated by this object. Just the identity and its multiples. So if you want to understand this as a functor, you can say that the category of finite dimensional Q vector spaces now embeds into the category of these Hodge-de Rham structures by mapping a one-dimensional vector space to V. Yeah, it's fully faithful. You have the same endomorphisms. They're both simple. It's just the same thing, written differently. And then you work out the formal periods. Okay. The actual periods, that's 3, right? 1 pi and log 2. These two periods here, they are linearly dependent. So I have a 3-dimensional period space, but the formal period space is 4-dimensional. I have 4 generators, and there aren't any relations that could identify things. The fact that I have the same entry twice is not something that the category knows. So it's not enough to have fullness to produce independence of periods. It's just not true. Okay, this was my counterexample. And it really does not look like the period matrix of a motive. It's all wrong. Luckily, we want the period conjecture to be true for motives, for the Hodge-de Rham structures coming from motives, so they really shouldn't, this one shouldn't be one. And it's not. So this is what the period matrix of a motive should look like. That's the correct order of these things. This matrix here, this period matrix, belongs to a motive that you, I think, all know. It's this is Motivic cohomology. So morphisms of triangulated motive, Q0 to Q1, so twist 1, shift 1. So H11, some people call it, or whatever the indices are. And this is always, over any field, this is K star. And then because I'm working with rational coefficients, it's K star tensor Q. And in this Hom group here, I'm taking the number 2. It's an algebraic, invertible algebraic number. So it gives me an element here in this Motivic cohomology. And then via the realization, that's the one from dm to d of mm. So this gives me one extension of Nori motives. So it's an extension of Q0 by Q to the Q minus 1. So I have a short exact sequence. Q0 and one end and Q minus 1 at the other end. And then we get the period 1, that's from Q0, and the period 2 pi I from Q minus 1. And the new period is log of 2. This is how log of 2 appears as the period of a one motive. So this is a reasonable period matrix for a motive. The counterexample is not. And why it's not? Well, because motives always have a weight filtration. That's a theorem of Arapura. All Nori motives have a weight filtration. And if I see periods coming up of 2 pi I and 1, then they can't be in the wrong order.
Maybe I have a question. Is it, can it be seen as a trace of the Bombardier weight filtration?
Yeah, that's how I understand the proof. use the byte structure in Bondaco and then push it to MM, and then that's how, and then you get the weight filtration on, So this is what you get from the weight filtration. If you can show the period conjecture for particular motifs, the ones that are one extensions of simple objects. So you need to show the period conjecture for pure motifs, and you need to show it for one extensions of simple motifs. Then you get the fullness statement. Okay, you don't get the period conjecture, but you get the fullness statement for the whole category of Nori motif. So what you actually prove is you show fullness and injectivity on X1 at the same time, and you do that by induction on the weight filtration. And if you want to do the exercise, you also need to use the fact that this category here has homological dimension 1. There's no X2. Oh, this is not difficult. So fullness follows from these special cases, whereas the period conjecture does not. If you look at the case of mixed state motifs, if you only look at one of extensions of simple ones, so one extensions of two tate twists, then the period numbers that we're talking about are powers of pi times the value of the Riemann zeta function in some integer. And this, what the period conjecture predicts is that these numbers are irrational. And that's, of course, much simpler than saying that they are all of them linearly independent. It's much easier. Still have fun, right? We don't know this. We don't know that these numbers are irrational. We're very far from that. But it's, of course, much, much easier than showing that all multiple zeta values are independent of each other unless we have an obvious relation. So, fullness is much easier than the period conjecture.
What happened to the log of 2?
Oh, it's not a mixed, it's not a, wait, what happened?
This looks like you're looking at like H1 Q of N over Q.
So what was my mistake? Oh.
This is for...
Okay, okay. So I can tell you what happened. So when the mixed state motifs I was looking at here, these were mixed state motifs over Z, right, okay. And then 2 is not in there.
Right. Great.
Yeah, so maybe it would be better to throw them in 2. Doesn't make it much better. The general principle is the same. Yeah.
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 I minus I bigger than 1 or something. Because zeta of 1 doesn't make sense.
Yeah, well, zeta of 1 in this business is so you go for the residue. Yeah. Okay. Okay. I can go a step further.
7 minutes.
Yeah, that's fine. Actually, when preparing the talk, I assumed that it would be 10 by now. But so we started with what the periods are and how they can be rewritten in terms of motifs, and then from the period conjecture you get a fullness conjecture for the Hodge-de Rham realization. And now we want to upgrade this to a functor on the derived category, to functor on DM, and ask about fullness there. So this was a conjecture formulated in a paper Andreatta, Barbera Viale, and Berta Pelle. And so they think not about the functors between categories, but more about the maps between the Motivic cohomology groups and its realizations. Like the original period conjecture was a statement about cycles mapping to classes in homology. So what they do, they look at a triangulated motif over Wygotsky motif over Q bar, Q coefficients. And then you have, this is my notation for Motivic cohomology here. So it's hom M to Qj shift I. And then you can apply the realization functors. So this this morphism turns into a morphism of realizations. In my diagram, I'm going from DM all the way down to the right. So morphisms in DM give me morphisms of Hodge-de Rham structures. And what I get are like global sections of HI of M twist J. Maybe it's minus J. It's oh, right. Yeah, plus or minus. Sorry, not sure about the plus or minus. But global sections. So the global sections, that's morphisms of the unit object to F. So you can work out what this means. Yeah, morphism of Q with the identity means that you have a class in V-de Rham and you have a class in the Q component, and they have to be compatible under the comparison isomorphism. In Hodge structures, these would be the Hodge classes. Yeah, so it's the analog of Hodge classes in this setting here. And they conjecture that this map is surjective. That can be reformulating by saying that if you take the composition from DM to Hodge-de Rham class structures, that this functor is fully faithful. Yeah?
I have a question. I see the fullness, but I don't understand why it should be faithful.
Oh, that's a mistake. Sorry. That's my mistake. That's a mistake on the slide. Full. Yeah, there's no way it could be faithful. No, sorry, that was my mistake. The conjecture that you have fullness on morphisms, well, it's morphisms of this special type, but then you have a tensor structure. So in the end, it's fullness for all Hom groups in the category. So is that a reasonable conjecture? Is it reasonable to expect that you get a full functor, not on Nori motifs, but now on triangulated motifs? And actually, yes, it is. It does follow from all the other conjectures that we have. So what do I need? Basically that the derived category of Nori motifs is the category of geometric motifs. You can get away with a little less, like you can ask that the singularization functor is conservative, but then that's nearly the same as asking that you have this, you need this kind of thing. Let's assume that Voivodsky motifs and Nori motifs are connected in the way that we hope they are. If there is a true abelian category of motifs, then this should be the case. Then assume that the fullness conjecture holds for Nori motifs. That was something that was reasonable because it follows from a conjecture that has been around for a long time. And then that's the additional piece of information that you need. You also need to know that in the true category of abelian motifs, the cohomological dimension is 1. There aren't any x2s. So it's not, when you do the computations, there's just a little bit more that you need, and then you can also make up assumptions that you really need an assumption like this. You need to know that there's no x2 in mixed motifs. And then you get the derived fullness conjecture. And all these things are expected to be true. So cohomological dimension for mixed motifs is expected to be transcendence degree of the field in positive characteristic and transcendence degree of the field +1 in characteristic 0. So we expect it to be okay. Yeah? We are over number field. So the arguments that I do there, they work because this is over number fields. The connection is much harder. So proving fullness in the derived setting will be even a lot harder than proving it in the Nori setting. But then we have better control about some of those motivic cohomology groups than we have about morphisms of Nori motifs. So maybe there are cases where you can do something. I don't know. Yeah, so this is the literature I'm referring to. There are a couple of books, and all the information is littered around it. But then this is a survey article, where I think most of the things, particularly the things about fullness, they're in that survey article. Thank you very much.
Okay, so before you ask a question, I'm supposed to give you the microphone. Comment on a dit? Yeah, so just a second. Okay, this is recorded.
So I think there should, for the Motivic fundamental group, there should have an action on the period. The Motivic fundamental group, if we...
Yeah, so if you, I was looking at abelian categories.
Yeah.
If you look at tensor categories instead, then you get their Motivic Galois groups coming in. And the period conjecture is equivalent to saying that there's a torso structure. It's like the torso of formal periods is connected, and it's a torso. Also, formal periods are a torso under the Motivic Galois group. That's a fact. And if you want the period conjecture, then actual periods have to be a torso. Yeah, that's true. So I didn't touch on that part, but yes.
Okay. So the statement is the formal period is a torso, the equivalent statement.
So you have, yeah. So this is like all formal periods for all motifs, and then you have to turn this into a scheme.
Yes.
And then you have the Motivic Galois group of Q bar operating on this. And this is a torso.
Yeah.
That's known by construction.
The period conjecture can be presented into some form of this.
It can be the one version. So we have you have a surjective map from P tilde to P, so you can formulate the period conjecture as saying that the actual period, spec of the actual period algebra is a torso.
Okay.
Yeah, you can formulate it this way.
Okay.
Yeah.
Yes.
When I stated it, I called it a proposition. That's because it's equivalent to this.
So, do we know how Nori motives relate to algebraic cycles and Chow groups? Is that
Nori motives to Chow groups. So we have Chow motives.
like for curves or something?
So if you do the Nori construction for Chow motives, you get Yves-André's motives, and pure Nori motives are André motives. So the Chow motives, Chow motives are something that sits inside the triangulated category. But then if you make it abelian, conjecturally you end up with homological motives, and then conjecturally these are the same as André motives, but without assuming any conjectures. If you make Chow motives abelian in a way that's compatible with the singular realization, you end up with the motives that Yves-André constructed by hand, and they are the same as Nori motives. So in that sense. And then cycles also give you morphisms in DM, so you get higher invariance, right? You don't only get things on pure motives, but you also get extensions. I have the Abel-Jacobi map. If the cycle class is trivial, then you get an extension of one motives, and that will be an extension of Nori motives, but there could be many more. We don't know anything about extensions of Nori motives. Yeah. So morphisms of Nori motives are not so bad, but extensions are really bad. Yeah.
Okay. So what's known about periods of abelian varieties? So you mentioned elliptic
H1.
Of abelian varieties.
Yeah, H1 of abelian varieties. They are one motives.
Yeah, but they are the tensor product.
About the tensor powers.
Yeah.
As far as I think, no, nothing.
Okay.
Yeah. As far as I know, nothing. Yeah.
And also, second question maybe. So it seems that this period conjecture implies transcendental transcendence
Yeah.
results.
Yeah, it does.
Is it possible to expect that one has pure Motivic proof of transcendence, or is it the other way around? This period conjecture depends on the techniques of Lindemann and so on.
So what I can tell you is about the case of one motives, where the formalism of one motives gives you a very good way of packaging things, and it gives you a very good way of formulating what the relations are. If you try to formulate the same relations just in terms of algebraic varieties, there are so many relations you just don't really see, because it's things that come up as maps of the Jacobian rather than as maps of algebraic curves. You can reduce it to the case of curves, but it's really, there's no way to understand what's going on. But the actual proof then needs a deep result in transcendence theory. So there's a really deep input from transcendence theory that was ready-made and was,
So it's the other way around.
Yeah, well, I think you have to have both. Because I think the statement really is motivic. If you try to do non-motivic statements of these same facts, yeah, you can avoid talking about the rationals. They're just pairs of natural numbers or something, yeah? But it's not a good idea. And I think it's the same with the period conjecture. If you try to do it without talking about motives, it's just, you're making life more complicated than it should be. So there was just one more.
I think one more question, because we don't have a break, so.
We don't have a break? What?
It's just kind of it's a similar question. So if you don't care about fullness, you already get relations coming from DM, basically. Are these relations new and interesting in some sense?
So when this was used, so you already, you know something about the generators, the dimensions of the space, have an upper bound from the space of generators, and whenever you have relations, then you know that it'll bring down the dimension of your thing. And this gives unconditional upper bounds for period spaces. And these are the results about multiple zeta values, like the linear Goncharov and Francis Brown, these people, what they did. They get upper bounds for these spaces of multiple zeta values by computing motivically. Yeah, you compute the actual dimension in that case. That's like the single case where the motivic picture can be computed, and you know what the dimensions are for formal periods, and then this gives an upper bound for actual periods. So yes, it does.
So let's thank Annette again.